Hello everyone, welcome to AVLSI lecture number 9, part number 1. So today we are going to start with a new topic, that is a common source amplifier with a triode load. So far we have seen common source amplifier with resistive load, common source amplifier with current source load, and now we are switching to the triode load. Now, where this is coming from? So basically what we are doing is we are trying to avoid using a resistor as a load in an integrated common source amplifier, because in an integrated circuit, we avoid using resistors. So we are trying to use a MOSFET as a resistor. So we know that in a MOSFET device, it can be operating in the triode region, can behave as a resistor R on, which we have already covered in lecture number 2.2. Let us revise that fact. Okay. So here was the characteristics wherein we can say that your MOSFET can replace resistors, right? And in the deep triode region specifically, as you can see over here, the expanded view is over here. So for very small values of VDS, you get a very current which is behaving linearly with the voltage. So this region is called as the deep triode region, wherein the condition is defined as the VDS value should be very much smaller as compared to twice VGS minus VTH. So under this condition, your MOSFET will behave as a resistor with the on-state resistance of R on. Now, I guess we have already derived the expression. Yes, we have derived the expression for R on, which is given by 1 upon mu n Cox W by L VGS minus VTH. So if you operate your MOSFET in the deep triode region, we can say that we can replace even a MOSFET as a two-terminal resistor. Okay, so that's exactly what we are going to do over here. Since your MOSFET can act as a resistor with a resistance of R on in the deep triode region, it can serve as a load in a common source amplifier. So over here, this is my common source amplifier with triode load, figure number 9.1, where M1 is the driver transistor and M2 is the load transistor, which is your PMOS triode load now. Okay, so let's just check whether M1 is suffering from body effect or no. Well, the bulk terminal or the body terminal of M1 is connected to ground, as well as the source terminal is also connected to ground. So VSB is 0. Similarly, for the PMOS, the body terminal is connected to VDD and the source terminal is also connected to VDD. So there is no body effect. That is VSB is equal to 0 for M1 and M2 both. Fine, that's a good news. Good start. Fine. So let's start analyzing. We have to make M2 work in the deep dive region, and we have to make the M1 work in the saturation region for it to work successfully as a common source amplifier. Now, what is the condition for a PMOS to operate in the deep dive region? So the condition is over here. Let me just slightly expand it. Yeah. So this is the condition for a PMOS transistor to be in the deep diode region. Its VSD2 value should be much smaller compared to twice VSG2 minus VTH2, mod of VTH2, right? And the second condition to satisfy is that VSG2 should be greater than mod of VTH2. Okay, so if your M2 satisfied this condition, we can safely say that it's operating in the deep diode region. Now let's move ahead. For M1 to operate in the saturation region, it's straightforward. VDS1 should be greater than or equal to VGS1 minus VTH1, and VGS1 should be greater than VTH1. Okay, fine. That's good to know. So these are the operating conditions for M2 and M1 transistor. So let's move on from here. Next is we wish to find the voltage gain of the circuit. So we have to draw the small signal model, right? So here we have already seen that if M2 operates in the deep triode region, it can be replaced by a two-terminal resistor R-on. So here, since the M2 is the transistor, we call it as R-on2. Fine. So we can easily replace this with a resistor R-on2, which is the small signal equivalent basically, right? And which is given in figure number 9.1.1. Clear about it? So it's not a physical resistor connected. It's just that your MOSFET is operating in the deep triode region. So it's behaving as a on-state resistance, which is linear. So that's why we have drawn over here R on 2. Now what do we do is we draw the small signal equivalent model for figure number 9.1.1. So first of all, we draw it for the transistor M1, right? So for the M1 transistor, it will be straightforward. We have the gate 1, source 1. Between gate 1 and source 1, we have VGS1. Gate terminal is connected to V in. Source terminal is grounded. And between the drain terminal and the ground terminal, we have GM1 into VGS1. Then we have RO1, and then also we have R on 2. Okay, because this is also going from the drain terminal towards the ground. Why? Because in a small signal model, your supply voltage, which is a constant value, will be zero. Fine. Because it represents the only small changes in the quantities, time varying changes in the quantities. That is a small signal model of your circuit. So there will be a resistor between the drain and the ground, and also the voltage is taken across the drain terminal and the ground. So yeah, this is my small signal model of the MOSFET. So have a look at it. If you have any doubt, you can ask. Okay, so we have to determine the expression of V out upon V in. So let's start. So I think we have done this many times, this kind of derivations. So we'll be a little quick over here. So your V out value is parallel to R on 2 and RO1. So the current flowing through R on 2 will be V out upon R on 2, and the current flowing through RO1 will be V out upon RO1, right? And now what do we do is we observe that V in is equal to VGS1, right? They are in parallel. So now we applied a KCL at drain 1 node, right? So we get all our outgoing current. So we get GM1 into VGS1 plus V out upon RO1 plus V out upon R on 2 is equal to 0. So that's what we have written over here. Then in the next step, we substitute VGS. We substitute VGS in terms of V in, right? So GM1 into V in plus V out terms, V out upon RO1 plus V out upon R on 2. So we club the terms together, right? And after algebraically solving, we get V out upon V in is equal to minus GM1 into RO1 into R on 2 divided by RO1 plus R on 2, which is nothing but your small signal voltage gain AV of a common source, stage, or amplifier with a PMOS triode load is given by minus GM1 into RO1 parallel to R on 2. So this is the expression for the common source amplifier with PMOS triode load. Now, this is using the standard technique by drawing the small signal equivalent model and then relating V out and V in terms. Now, we can directly write the expression of gain AV with inspection, right? We know the general form of the expression wherein this was a resistive load, actual resistor was connected. So what was the formula? AV was equal to minus GM into RO parallel to RAD, correct? In this case also it's the same. Instead of RAD, we have R on 2. So what will be the gain formula by inspection? It will be minus GM1 into RO1 parallel to R on 2. So there can be a very conceptual question of 1 marks or 2 marks, right? They might have given you the value of R on 2, RO1 and GM1, and they they will ask you the value of gain AV. So in those situations, you need not sit and derive the entire formula. You can write the formula by inspection. So it will be minus GM1 into RO1 parallel to R on 2. Here the output impedance is very obvious. It is RO1 parallel to R on 2. Okay. So this completes the derivation. So let's have a glance. So we have started with a common source amplifier with a triode load, and we have determined why a MOSFET operating in the deep triode region can behave as a resistor, right? And then we saw the conditions for the M1 and M2 transistor to be in their respective operating regions. And then we started building up the circuit with respect to the small signal model. We have replaced the M2 transistor, which is working in the deep triode region, as a resistor, on-state resistor. We plug in that value. We have put this value over there in the small signal model. And finally, we derived the relation between the V out and V in terms. So finally, the small signal voltage gain was given by minus GM1 into RO1 parallel to R on 2. Okay. Now, one more thing which we need to remember. Let me go back to the a little bit bigger font. So R on 2, value of R on 2. How do we calculate? When M2 is operating in the deep triode region. So here is the formula given to us. R on 2 will be given by 1 upon mu p into Cox into W by L of 2 into VSG2 minus mod of VTH2, right? And over here, from the circuit diagram, can we say that your VSG2 is equal to VDD minus VB? Let's just check it out. So what is VS2? VS2 is VDD. And what is VG2? VG2 is VB. So VSG2 will be VS2 minus VG2. That will be VDD minus VB, right? So this R on 2 expression is modified as follows. It is 1 divided by mu P Cox W by L of 2, W by L2 into VDD minus VB minus VTH2. So this becomes our equation number 9.2. Now, yeah, clear about this? Let me keep this for some time. Okay, so let's move on now. Next comes the biasing conditions. So biasing conditions means choosing the proper value of VB and the biasing voltage for the M1 transistor. So your biasing voltage over here VB should be selected such that your M2 transistor remains in the deep triode region, right? So for the M2 transistor to remain in the deep triode region, the condition is that VSD2 should be lesser than twice VSG2 minus mod of VTH2. Okay. And from the diagram, we can say that what is VSD2? It's VDD minus V out. You can check it out. VS2 is VDD and VD2 is V out. So VSD2 is VDD minus V out. Also, earlier we have determined VSG2 is VDD minus VB. So we'll plug in both the values right over here. So what do we get? VDD minus V out should be lesser than twice VDD minus VB minus mod of VTH2. Okay. So we'll club the terms of, we isolate the terms of VB on the left hand side and rest all the terms on the right hand side. And finally, we get the condition that VB value should be much less compared to half into VDD minus twice mod of VTH2 plus V out. Okay, this becomes our equation number 3. So this is the condition on VB, biasing voltage. It is very small value and it has to be very much precisely less than this value given in equation number 9.3. Okay, so yeah, this is the note over here that the gate of M2 is biased at a sufficiently low level, ensuring that the load is in the deep triode region for all the output voltage swing. So that is what we have to make sure. So it's very difficult to precisely, select the value of VB such that your M2 transistor remains in the deep triode region. Okay, so clear about the biasing conditions. Let me keep this on the screen for some time. Okay, fine, good. So let's move on and go to the next part of this section. Okay, so over here, the question number 1 is that estimate the maximum output voltage swing for a common source amplifier with triode load, right? So we know this is my common source amplifier with triode load, correct? So the circuit looks familiar, almost similar to common source amplifier with current source load. So what is the difference between them? The VB value. So in the earlier case for the current source load, VB is selected such that your M2 is in saturation. And now with the triode load, VB is selected such that your M2 remains in the triode region. So we have to determine the output swing, output voltage swing. Now remember, output voltage swing, we have a term over here right now. We will be using this term very often, voltage headroom. So output voltage swing is also called as voltage headroom. Now over here, we have already written the result, but we will have to, intuitively refer that its value is coming this only. So here the V out max is coming out to be close to VDD and V out minimum is coming out to be close to V in minus VTH1. So let's see how we got these values. So your maximum output voltage is near VDD. Let us see how. So your M2 transistor, it's in the deep triode region. And when it is in the deep triode region, your VSD2 value is very small. Also evident from this equation, it should be very small compared to twice VGS2 minus mod of VTH2. So also VSD2 value is also given by VDD minus V out. Okay, because VS2 is VDD and VD2 is V out. So VSD2, it's very small value and it's equal to VDD minus V out. So if VSD2 is very small, we can consider approximately very small, close to zero. So hence what do we get? V out is approximately equal to VDD. Fine. So that's why we can write over here V out max as approximately equal to VDD. It's not equal to VDD, slightly lesser than that. Okay. So let's check the condition for V out minimum. So the minimum output voltage is near V in minus VTH1. So that is happening when the M1 transistor is working at the edge of saturation. And what's the condition for that? VDS1 should be equal to VGS1 minus VTH1. So over here, VDS1 is V out and VGS1 is V in. So we can very straightforward write that V out is equal to V in minus VTH1. So this is the minimum condition of V out minimum. So that is V in minus VTH1. Hence the output voltage swing is between VDD and V in minus VTH1. Okay, that is your V out max and V out minimum. So if someone wants to write the peak to peak value, what it will be? V out max minus V out minimum. Okay, remember one more important thing. Output voltage swing is also called as voltage headroom. From now on, whenever we use this, is the output voltage swing. Okay, so you can have a look at it. I'll keep this steady for some time. So we have estimated the maximum output voltage swing for a common source amplifier with triode load. So we have determined V out max and V out minimum. So kindly have a look at it. If you have any doubt, you can post your queries in the comment section. Okay, so let's move on now. So there are some advantages and problems associated with common source amplifier with triode load also. So let's start with an advantage. I mean, it's a disadvantage and an advantage also compared to earlier cases. So we have a low static power dissipation. Okay, that's an advantage, but in prospect to the integrated circuit, it's a disadvantage, because in an integrated circuit you don't want static power dissipation at all, right? So let us see the diagram over here. So M2 is in the deep triode region. When it is in the deep triode region, it draws very less current. Okay, that means your power consumed will be lesser. So hence we can write over here low static power dissipation, which is a kind of an advantage over the saturated load and the resistive load. But with respect to the integrated circuit, it's poor actually. Now, R on 2 depends upon mu P into Cox, VB and VTH2 from 9.2. So let us see this 9.2 equation. Yeah, 9.2 equation. Yeah, R on 2, it's inversely dependent upon mu P into Cox. We also depends upon W by L of 2, VB and VTH2, right? So all these terms here R on 2 depends upon, right? So all these values, that is mu P Cox, VTH2, vary with the process parameters or the process fabrication parameters and the temperature. And if they vary, the R on 2 value will also vary, and that will affect the performance of the chip or the performance of the device. Then generating a precise value of VB, it's a challenge. It's a difficult to design. You require an external extra circuit requirement for generating the value of VB, and which is difficult to design and use. Okay, now also we saw that R on is inversely proportional to W, and it's directly proportional to L. Let us see that. R on, right? Yeah, as you can see, it's directly proportional to channel length and inversely proportional to channel width. Okay, let us see what point we are making over here. The point we are making over here is that if you decrease the value of channel width, your R-on will increase and your voltage gain will increase. But there is a limit. You cannot go on decreasing the value of channel width. It has to be within a limit. Okay, so one advantage over here is that R-on can be increased by reducing W, and hence the gain can be increased. That's one advantage. But the problem is that W cannot be decreased indefinitely lower value. It has to be within a limit. So that's why we cannot increase R-on to a higher value over here. Hence your voltage gain is also limited. So the solution for this is to use a saturated load, right? Then we have a lower voltage swing. We just now saw in the earlier question that we don't get a full voltage swing from VDD to zero. In fact, it's a poor voltage swing actually. So we have a lower voltage swing, which is a problem, which is a issue. Then the last one, it's the voltage gain variation with the input signal amplitude. So here also in the gain formula, we have GM1, and in the GM1, we have VGS1, and VGS1 is nothing but V in. That means my voltage gain depends upon the input signal level, which will definitely lead to non-linearity, which is a problem. So these are the various advantages and problems faced in a common source amplifier with triode load. So have a look at it. I will keep it there for some time. Okay, so I guess we have come to the end of this session. So today we have started with a common source amplifier with triode load. We have derived its small signal, the small signal voltage gain expression, and we have seen its biasing condition. We have also determined the output voltage swing, and at the last we have also seen the advantages and problems of the common source amplifier with triode load. Okay, so that is all for this session. Next time, we will cover the numerical based on the common source amplifier with triode load. Until then, have a good day and thank you.